Okay, we're going to work with the concept of rotational equilibrium. The main idea is that rotational equilibrium occurs when all torques are nullified with each other, torques being the responsibles for making objects rotate. So if different torques combine cancel each other, that means there is no interacting force that will make an object rotate. In other words, the object won't rotate, there will be a rotational equilibrium. Or if the object was already rotating, there will be a permanent normal state of rotation, or a steady rotation, in other words. Rotational equilibrium therefore will be described by the following formula, which means the sum, or which says that the sum of all torques must be equal to 0. That is the only way we can guarantee that we have rotational equilibrium, otherwise we don't have rotational equilibrium. We're going to solve exercises where equilibrium will be something that is assured. So knowing that we have equilibrium, we can use this formula at any given moment. The main process we're going to follow is we're going to find each individual torque, which are the ones we need to add. We're going to perform a rotational equilibrium analysis based on this equation, and if necessary, we're going to use translational equilibrium analysis, but only if we need it. The consideration we need to have in this case is that all units must be in accord to the international system, being mass in kilograms, distance in meters, and force in newtons. Most importantly, we're going to focus on meters and newtons because those are the things we need to find torque, being the force and the lever arm, the things that we use there. So let's try to apply this concept here. Exercise number 1 tells us to calculate the measure of force F. F is a force. We don't know what is the magnitude of this force. We're going to figure it out. What do we know? Okay, the lever arm of F is 30 centimeters. And we also have an object in here with a specific mass. If an object has a given mass, then we know that there is always a gravitational force that is pulling the object down. That will create a new force that will be called gravitational force, and based on that force we can make an analysis of torque with 2 torques. The lever arm for this object is 0.2 meters. So with this information, what are we going to do first? First, we need to make sure that all the units are in accordance to the international system. And in this case, the 30 centimeters we have here are not in meters, so we're going to start with that. We're going to convert those 30 centimeters to meters. So I'm going to write here convert, and I'm going to put 30 centimeters. I'm going to convert that with 1 meter is 100 centimeters. I cancel centimeters, and that will give me 0.3 meters. So instead of 30 centimeters, we're going to use 0.3 meters. Next, we need to convert this, well, not convert, but to obtain the weight of the object, because we're going to be working with forces, not with mass. So we need to find the gravitational force. The formula for gravitational force is, or for weight, is mass times gravity. Pretty simple. So we substitute the mass, which is 20 kilograms, and we multiply with gravity, which is 9.8 meters per square second. So gravitational force will be, in this case, 196 newtons. So we have 2 forces. That means we're going to have 2 torques. None of the forces is applied directly on the fulcrum. We're going to ignore those. So in this case, we have 2 torques that are useful for the analysis. Torque number 1 would be the generated by F. If I follow this path around the fulcrum, you can see that this force will create a positive torque. So I know I have a positive torque in here, and torque is force 1 in this case times lever arm 1. The first force being F, the lever arm being 0.3. Since it's positive, I'm not going to put any sign in there, and 0.3 times F will be 0.3 F. Then the second torque. Second torque will be the generated by gravitational force. Gravitational force pulls down. So if I follow that trajectory around the fulcrum, I can tell that this will create a negative torque. So I have a negative torque in here. Torque in this case is force 2 times lever arm 2. Since it's negative, I'm going to put a minus, and I'm going to put F2 being the gravitational force. So that will be 196. R2, or the lever arm for this, will be the 0.2 meters. So I'll put in here 0.2. 196 negative times 0.2 will give me negative 39.2 newtons per meter. So those are the two torques that I have. What am I going to do next? Well, I'm going to analyze with the rotational equilibrium formula. So I'll write rotational equilibrium. I know that means the sum of all torques must be 0. So I'll add all of the torques. In this case, it will be 0.3 F plus negative, which means minus 39.2 newtons per meter. That will be equal to 0. I can easily find an answer in here by just moving the 39.2 to the other side, and then I pass to divide 0.3. And if I divide those things, that will give me 130.6667 newtons. And that will be the answer for the exercise. So, exercise number 1 will be solved that way. Let's do another one. Exercise number 2. In this case, we have two unknown forces, A and B, and we're going to find them. All of the units are correctly in the international system, so no conversions need to be done. Now, in this case, B is a force that is applied directly on the fulcrum. I know that the torque for this thing will be 0, so I'm not even going to consider to use B in this case for the rotational analysis. I'll use 35, A, and 20. That means I have 3 important torques to consider. Let's start with 35. So torque 1 equals, if I follow the trajectory of the force and I move it around the fulcrum, that means this is a positive, or this is going to generate a positive torque. So I know I have a positive torque, F1 times R1. So the first force is 35 newtons. The lever arm for 35 will be 6 meters. 35 times 6 will give me 210 newtons per meter. Then let's go with the torque number 2. Torque number 2, remember B doesn't count because we already know it's 0 because it's applied directly on the fulcrum, so there is no torque in there. I'm going to work now with A. If I follow the trajectory around the fulcrum, I can tell that this will create a negative torque. So the torque in here will be negative. Force 2 times lever arm 2. The second force, since this is a negative torque, I'll put minus. The second force is A. And the lever arm for A, from A the distance is 4 meters to the fulcrum, so is A times 4. This will give me negative 4A. The torque number 3. Torque number 3 follows the same trajectory. That means this is also a negative torque. I'll use F3, R3. Since it's negative, I'll put minus. The third force is 20 newtons, and the lever arm for 20. From this force to the fulcrum, the distance is not 3, it's 7. So minus 20 times 7 will give me minus 140 newtons per meter. Okay, newtons times meter. Those are the 3 torques that I need to consider. Now I can make an analysis of rotational equilibrium. So rotational equilibrium will be the sum of the torques has to be 0. So 210 plus negative 4A, or in other words minus 4A, plus negative 100, which means in other words minus 140, equals 0. Okay, I combine all of the 3 torques, and this is a linear equation that you can easily solve. So you just move these things around, and you find A by passing to divide minus 4. So minus 70 divided by minus 4, that will give me A. A equals, in this case, 17.5 newtons. Okay, so I found A. Now the problem in here is I also need to find B, but I cannot use B in the torque analysis because the torque for B is 0. So what should I do to find B? I'll use, in this case, since I cannot use rotational equilibrium to find B, I'll have to use translational equilibrium in this case to find B. So translational equilibrium analysis, in this case translational equilibrium, since we have vertical forces, which are going up and are going down, I'll make a vertical analysis. I don't need to make a horizontal analysis. This vertical analysis means up equals down. That will be a vertical analysis of translational equilibrium, being the upward force only B, and the downward forces being 35, A, and 20. Now I know that A is 17.5, so I'm going to substitute that. B equals 35 plus 17.5 plus 20. Once I have that, I just need to add, and that will give me 72.5 newtons. That will be the magnitude for the force B. I found A, I found B, I already solved the exercise. That's how we do it. Let's do this one next. In this case, I'm not looking for force, I'm looking for a lever arm or a length. I'm trying to find this distance. So let's do the same type of analysis that we've done. We need to check first the considerations. We need to understand if we have all of the units in the correct international system. In this case, there's one that is not working for us, 12 feet. We're not going to use feet, we're going to use meters. So we need to convert that first. So let's convert 12 feet to meters. In order to do that, we're going to multiply with 1 meter over 3.28 feet. Feet are going to get cancelled, and if I do this operation, this will give me 3.6585 meters. So instead of 12, I'm going to use this data. Now let's find the torques. There are two torques in here. Torque number 1, if I follow the direction of the force around the fulcrum, I can tell that this is a negative torque. And the force number 2, if I follow that force around the fulcrum, that will give me a positive torque. So the first one will be negative, the second one will be positive. Torque 1 will give me a negative torque. It's F1 times R1. Okay, let's change this thing. It has to look more like a rotation. Yep. F1 times R1. That means minus. The force 1 will be 31 newtons, and the distance or the lever arm is 3.6585. If I do this operation, it will give me negative 113.4135 newtons per meter. Then we're going to find torque number 2, which gives me a positive rotation, F2 times R2. So since it's positive, I'll just put 20 times R2, which is X, so 20X. Let's make the rotational equilibrium analysis. So rotational equilibrium. Rotational equilibrium means the sum of all torques must be 0. So which torques do we have? We have negative 113.4135 plus 20x. That has to be 0. So I just move this to the other side. 20x equals 113.4135, and I pass it by 20, so x equals 113.4135 divided by 20, and that will be x equals 5.6707 meters. That will be the answer for x. So we did it. We found the distance that we were looking for, or the length that we were looking for. That's how you do exercise number 3. Let's do one more. In this case, we also have a force that is being applied directly in the fulcrum. That means A will generate no torque. I'm just going to consider 80 kilograms, and B define torques. Torque 1 will be in this direction, which is negative, and torque 2 will be in this direction, which is positive. Now, let's start with the considerations. Are all units in the international system? Yes. Second consideration, this thing is not a force, it's a mass because of the kilograms. We need to convert it to a force, to a weight. So let's apply the formula for gravitational force, which is mass times gravity. Gravitational force in this case will be 80 kilograms times 9.8 meters per square second of gravity. If I multiply those things, that will give me 784 newtons. So that is the measure of the force in here. Now that I know that, let's find each one of the individual torques. Torque 1, like I said, is negative. F1 R1. So minus, the force is 784, and the lever arm in this case is 2.5. That will give me an answer of negative 1960 newtons per meter. Next, we're going to find torque number 2. So torque 2, as mentioned before, will be a positive torque. So it will go in this rotation, F2 R2. So positive, the force 2 being B, and the lever arm in this case is the distance from B to the fulcrum. What is the distance? It's not 3, is 5.5. 5.5 meters. So if I multiply that, it will give me 5.5 B. Those are the two torques that are going to be acting with each other in here. The other one is 0, so I'm not going to consider it. Rotational equilibrium. This means the sum of the torques must be 0, being both torques negative 1960 plus 5.5 B. With this, I can easily find an answer. 5.5 B being equal to 1960. B equals 1960 divided by 5.5. And that will give me an answer for B of 356.36 newtons. So I found B. How do I find A? Since A is nullified when we're talking about torque, we need to make a translational equilibrium analysis. So that's what we're going to do. Translational equilibrium. Being in this case upward forces equal downward forces. I have two upward forces, which are A and B, and I have one downward force, which is 784. So A plus B must be equal to 784. So I'm going to substitute B, and I'll put A plus 356.36 equals 784. Next, what am I going to do? Well, I'll move that, I'll pass it to subtract, so A equals 784 minus 356.36. If I do that subtraction, A will be equal to 427.64 newtons. So I found B, and I also found A. That will be the solution for this exercise. Now let's do one last exercise. This one is interesting to solve. Find the magnitude of the unknown forces. In this case, we have two unknown forces, A and F. Now, since 80 newtons is being applied directly at the fulcrum, that means the torque of 80 newtons must be considered as 0. Let's work now with the things that we know. The considerations tells us that we need to work with international system units. 50 centimeters and 20 centimeters are not in international system units, so we need to convert them. So we're going to convert each one of them. 20 centimeters to meters. That will give us 0.2 meters. And 50 centimeters to meters will give us 0.5 meters. The rest of the units are in accordance, so we can proceed with finding each one of the individual torques. So let's start with the first torque, torque 1. I need to follow the direction of A force around the fulcrum. That tells me that this is a positive torque. Then I'll analyze F, and notice that F around the torque will give me a negative torque. So the first torque will be positive. So F1, R1. The force in this case will be A, and the distance from A to the fulcrum is 0.7 or 70 centimeters, or 0.2 plus 0.5. So A times 0.7. That will give me a torque of 0.7 A. Next, torque 2. The second torque we already discussed, that is negative. Not in this direction, in this direction. Negative. So F2, R2. I put the minus, and the force in this case will be F, and the lever arm from F to the torque will be 0.5. So I'll put 0.5 in there, and I'll get negative 0.5 F. That's it. I have both torques. So let's make the rotational equilibrium analysis. Rotational equilibrium analysis. Rotational equilibrium states that the sum of all torques must be 0 in order to have equilibrium. So if I combine both torques, that will give me 0.7 A plus minus, so minus 0.5 F, and that has to give me 0. Now, since I have two levers or two variables in this equation, this is impossible to solve. I cannot continue in here. So what do we do if we cannot continue? Well, we work with translational equilibrium. That might give us something else. So, translational equilibrium. Translational equilibrium, in this case of vertical analysis, states that upward forces must be equal to downward forces. So, let's see, what do we have here? Okay, the upward force that we have is F, and the downward forces that we have is A and 80. So, let's do this. I have F in here equals A plus 80. I also have two variables in this equation, so it is impossible to solve. But notice now that I have two equations. With these two equations, I can create a system. I'll move intentionally A to the side in the same order than the first equation. So if I move A here, it will be minus A. That will give me minus A plus F equals 80. I move it this way so that I have A first, then F. That way, I also have here A first and then F. Since I have them in the same order, I can put them together, and I will get this, 0.7 A minus 0.5 F equals 0. And the other one will be minus A plus F equals 80. What is this? This is a system. Since I have a system, I just need to solve it, and if I solve the system, I will easily find A and F. So let's solve the system. How do we solve these things? Well, we switch the numbers, or we flip, in this case 1 in here, 0.5 in here, and I multiply. So 0.7A minus, you could check how to do systems, and then here minus 0.5A plus 0.5F, I multiply, and 80 times 0.5 will give me 40. I draw a line, F gets cancelled. 0.7 minus 0.5 will give me 0.2 A equals 0 and 40. Well, that will give me 40. And I pass the 0.2 to divide. So A equals 40 divided by 0.2. Dividing by 0.2 is the same as multiplying with 5. So the answer will be 200. Now I know that A is a force. So the unit for 200 will be 200 newtons. Don't forget to put the units every time you get an answer. What do I do next? Well, I'm going to use these equations, one of these ones, and I'm going to substitute. We normally use the first equation, but the second one looks easier, right? Since the second one looks easier, I'll use the second one. So I'll copy minus A plus F equals 80. Minus, what is A? A is 200, so I'll substitute A with 200. Minus 200 plus F equals 80. I just need to move minus 200, so F equals 80 plus 80 plus 200, and F will be equal to 280 newtons, because F is also a force. Now notice that I found A and I also found F, and those two were the things that we were looking for. So that's the way how we can solve this type of exercises using the concept of rotational equilibrium.